start the session. So maybe they hear me. I don't think they will. They're out in the sun or playing somewhere else. Just one technical announcement, which has been made already many times, but if you have a mobile phone, please switch it off. Not only because it can ring in the middle, but if it does ring, it interferes with the broadcasting system. So people looking at us outside on the network see a number of bunch of nicely colored stripes, etc., etc. So thank you for that. What are we here for this afternoon? We are talking about advanced applications. We are talking about two possible edges of the world, which at least are looking to go closer and closer and possibly merge together in the very near future. From many of us started to say that television wants something and networking and video conferencing wants something else. But as you will see this afternoon, many of the techniques which are applied in television are going to be applied for video conferencing and networking, and vice versa. Television producing bodies are thinking of using the network for their purposes and has a major device and support media for their current tasks. So this is also an interesting area of the new application where quality of service and guaranteed bandwidth is needed, because of course when you are trying to look at the video conference, you can afford maybe to lose a few segments of the video. You are a bit annoyed if you don't understand what is being said because you lose voice. But if you are trying to use the network to see television, then you will be very annoyed if you miss the most important scene of the film because of that. We have three speakers this afternoon. I will try to introduce them briefly. The first one is Ahmed Meddahi. I hope I pronounced it right. And he is a research engineer at ENIC, which is a research institute in France for advanced network application. And one of his major tasks is distance learning, as distance learning is something which has got to do with remote presence and video conferencing. This is the traditional approach of the video conferencing program on the network. Ahmed, the floor is to you.
Thank you. Good afternoon. So my presentation deals with specific issues we face through the development of application at ENIC, distance learning application, and specifically, more precisely, mobility issues. In fact, we think that the ability to develop our own application, distance learning application, give us the possibility to adapt the technology to our pedagogical constraints and not the reverse. So the content of my presentation will be this one. So after a brief introduction to expose the context, I will present an existing and new tools under development and used by ENIC for distance learning. One based on IDN technology, the other one on internet technology. We will also analyze some sensitive issues in terms of mobility and how new protocols, essentially SIP, Session Initiation Protocol, can provide a solution before concluding. So just a few words about ENIC. ENIC University is located in north of France. ENIC has been created in 1990 by a partnership between the University of Lille, located also in north of France, and the National Institute of Telecommunication based in Paris. ENIC delivers an engineer degree in information and communication technology. There are, as you can see, three main channels, training channels. The first one, the initial training takes 5 years with about 330 students for the year 2000. The second one is the local or on-site training channel for adult people. And the third one, and most recent one, is the distant or remote training channel, also for adult people. This training channels are called Tutelvisio. This is a name we gave because Tutelvisio use mainly ISDN technology, and Tutelnet is the tool using internet technology. We notice that in terms of student number growth, the initial and local adult training is quite stable, while the remote distance training channel increased. We had around 70 students last year and around 50 students in 1998. The reason is that more and more people, technicians, essentially find this type of formation adapted to their professional constraints, as they still work in their company during the main part of their formation. So we consider that there is a real need for distance learning service. Distance training has begun at ENIC in 1996. That means we have begun to work on the technical and pedagogical aspects from about 1992. This leads us to improve and make important efforts in pedagogical engineering and in order to design the technology for an efficient formation, especially for distance learning. So ENIC activities are mainly research and development in different fields related to telecommunication, also in company training and pedagogical engineering. So, as I told you before, we conduct research and development in the field of distance learning services. ENIC developed a first architecture based on ISDN and H320 protocols called Tutelvisio. The main component for this service are a student studio with different kind of equipment and software, an audio-video system with a pan-tilt camera controlled by specific software, question and answer system controlled also and managed by specific software and hardware. Also a lecture studio with an audio-video system also controlled by a software, and a quite a user-friendly graphical user interface for managing the lecture. I mean the interactivity with the students and also the management of the different sources, audio or video sources for the lecture. And finally, we have also a collection of softwares and protocol for controlling the system and for communication between the remote and the local site. On this slide, you can see the architecture, in fact, of Tutelvisio, which is the system used for distance learning based essentially on ISDN technology. Here we use internet only for data transmission. Okay. So we use internet for data and command transport between the different sites. So this slide shows the graphical user interface used by the lecturer for managing and controlling the distance lecture. The top part of the screen enables the lecturer to choose and send a source for illustrating the lecture, for example, an audio or video tape or satellite emission. And the bottom part of the screen enables the lecturer to manage the remote pan-tilt camera and the question-answer system. In fact, to manage the interactivity with the different students. So we have some remark containing this architecture. So the main benefit of this architecture are a quite good video quality provided, and performances also in terms of throughput, as we use ISDN and H320 protocol, which assure a certain quality of service for multimedia application. Nevertheless, there are some drawbacks. We face still today some interoperability problems, mainly containing the transfer of asynchronous data. That's why we use internet for transmission of asynchronous data. Not too much for video or audio transmission. The protocol is quite stable and compatible for this kind of sources. But this architecture is quite difficult to deploy for individual or self-training services, I mean for large-scale deployment, and also the deployment cost, which is quite an issue. We don't have ISDN access quite widespread as internet access. So, following the development of Tutel Visio, ENIC is using and developing a new service and architecture based on internet technology called TutelNet, as you can see on this slide. The main component for this service, in fact, is a web server. This server uses HTML and SMILE technology and contain ENIC web courses for asynchronous lecture. This server is also called lecture and on-demand server. Also, we have a streaming server working with the web server, which stores audio-video lectures for asynchronous lectures or lecture on demand. It is also used for accessing live audio-video lectures for synchronous lectures. Also, a multi-point conference unit for video conferencing or audio conferencing in the context of synchronous lectures, and a specific or proprietary server called Tutel server used for live data conferencing. This is a specific multi-unicast software based on Java and C++ technology with functionalities for synchronous lectures. So here you have the different components. Also, this is not enough. On the client side, we need also a client to access to the service. So the client agent, in fact, is a client software used by the student for accessing live or store lectures, and also a client software used by the lecturer for providing and managing live lectures. These client agents consist of a collection of different software, a web browser we use for accessing, a streaming client or player for accessing to the streaming server, sometimes H323 client for voice over IP, and also specific client, Tutel browser and Tutelcast for data conferencing. So here you have the graphical user interface of the Tutelcast client used by the lecturer for data conferencing. With these tools, the teacher can broadcast slides, messages, and makes annotation in real time. And this other slide shows the student side. So this is the graphical user interface of the Tutel browser software used by the student to receive slide, teacher's annotations, and for communication during the live session or lecture. Of course, as I told before, besides this specific software, the client, students, or teacher may use other clients like web browser, streaming client for audio-video communication, but with a random quality in the context of an internet. So this interface shows the integration using ActiveX technology of these different clients in the single interface to minimize the number of separate interfaces. So today we have this architecture, one based on ISDN technology, mainly H320 protocol. This is Tutel Visio. And another one based on internet technology. This is TutelNet. The services today are not connected and are considered independent. But in short term, we will have to interconnect and interoperate these two architectures in order to provide the same distance learning service to students or lecturers, whatever access technology or systems they use, ISDN or internet. So, again, we have a few remarks concerning this platform. As I told before, TutelNet, so the tool based on internet, makes the service available from a large number of clients. Nevertheless, there are still some issues. The first one concerning H323 interoperability and interworking. We still face protocol and compatibility between different vendors today. There is also a big issue concerning the interworking across firewalls. Today, many firewalls which have been deployed filter traffic based on access list, port numbers or IP address, and they are not full state in order to recognize specific flow like H323 flow or other flow. So the only way to assume today H323 interworking is to negotiate with the security administrator and in order to open all TCP and UDP port beyond 1024 with security issues that generate. Also, access heterogeneity presents an issue. Effectively, clients may access to the services via different type of connection. ADSL, mainly fast modem, V90, or low modem, so they don't have the same level or quality of service for the same session. This creates pedagogical problems. Today, the internet-based effort shows that the performances, delay, jitter, and so on are not enough for application requiring interactivity. So today, merging audio, video, and data all together on internet is not acceptable. That's why we maintain different kind of access for the same service. For example, internet for data conferencing and PSTN or ISDN for audio or video connection. Also, another problem is the server content, the server which contain the lectures, the resources. These servers are centralized. They could be overloaded and not accessible for a certain period of time. So there is a need to duplicate the content and put the servers close to the client location. Also, interworking between TuteleNet and TuteleVisio become a challenge and support the proper interworking and interoperability between different protocols like H323, H320, and future other protocols. We need also better access control, and not the last one, but the major issue is that most of the clients connected to our service use a private IP address numbering plan and use NAT system, network address translation. So two clients from different sites may have the same IP address and port numbers. That is an issue for client identification and differentiation at the service level. So, from our point of view, mobility in the context of distance learning is one of the most sensitive issues. Effectively, we may have two types of mobility. Mobility at the service level, I mean that the lecturers may be in his office, laboratory, or outside, and he wants to be able to give his lecture from anywhere. Students also may be located at school, at home, or in his job office, and he wants also to access to distance learning service, live lectures or lecture on demand from anywhere. Another point also is that location of servers and content may change. So this is the service level mobility. There is also another level of mobility. This is the IP level mobility. So clients, as I told before, who are outside the university generally have dynamic IP address from their ISP, from their provider. Also, IP address translation may occur if the client is connected via network address translation, as I told before. So, a protocol like SIP, Session Initiation Protocol, can provide a solution for dynamic IP address and mobility issue. I will explain later how. So, SIP messages, particularly SIP headers and SIP messages body, can provide a solution to describe quite precisely the type of service or lecture the client wants to access, with many attributes. I mean, for example, start time, for how long you want to access to the lecture, and so on. For example, using some specific fields like subject or expires field in SIP messages. SIP may also provide enhanced services like forking, multiple invite, call forward, and so on, which are quite well adapted in this context of mobility. Also, SIP can be used independently of the media stream transfer protocol. As you have seen before in the previous slide, there is a need for true signaling and call control protocol in our architecture, besides the media stream protocol we use, which can be proprietary. So, just this slide give a brief resume of the SIP protocol. So session initiation protocol is defined in the RFC 2543 by the IETF Music Working Group. SIP is a signaling protocol used for connection establishment. It doesn't deal with media transfer protocol, media transfer. SIP is a textual and client-server oriented protocol, and the main structure of SIP messages consists of a start line which specifies the type of request or the status of the response. The second line, the line after are the headers. So we have many types of headers, a general header, request header, and entity header. After we have a blank line, which is a separator with the message body itself, which specifies some session attributes, for example, using for example, the start time of the lecture and so on, using session description protocol. So, if we adapt this protocol in our context, in fact, we need two new servers in our architecture. What it is called in the SIP terminology, register server database, and another one with we put this function on the same server. This is the SIP proxy function, a redirect function, and a specific proxy function we call tutel proxy server. So two new servers in our architecture. So here we will see a different scenario how we use SIP in different contexts of lectures. So the first scenario concerns the access to a live or asynchronous lecture. So in this case, in fact, client, so lecturers or students, so will first register to the register server or database. So the registration message contains, as I told before, many attributes. The client IP address, at the moment, the name and lecture code to identify the requested lecture, to identify what type of lecture the student wants to access, the duration, and other attributes for the session. So, after the registration step, the connection establishment occurs. The invite message coming from the lecture agent will be sent to the proxy server. This is what it is shown on this slide, on this step. The fields contained in this invite message and the request to the register database enable the proxy to redirect the invite to all client agents. So this is this step. We make a request to the database to have all the IP address of all the location of the client. We have the answer of the database, and after the proxy server can send a multi-unicast invite message to all students here, okay, concerning by the lecture. This is the first scenario. The second scenario, so this is a data stream following the connection establishment. The second scenario concerns the access to a asynchronous or to a stored lecture. In fact, the access to the lecture on demand server, what we call lecture on demand server. So in this case, the first invite message sent to the proxy is used to find in the redirect database the appropriate server the server in terms of content and location, depending on different criteria like the type and lecture or lesson identifier, also on the location of the invite request sender. So this can be done by analyzing some fields in the SIP header message or certain SDP values in the message body, for example, the phone number field, the honor field, or others of the SIP invite message. So after the moved response coming from SIP proxy will provide to the client the appropriate server location and other information. For example, the locking password for accessing to the server, we can provide this to the student for the session. Also, we can provide the session duration and so on. So following the response, the client can now directly establish a connection to the server content. So the register database and the SIP proxy provide a kind of access control to the services or to the different servers. Of course, this SIP proxy does not preclude a direct connection to the service. If the client knows the address of the server, he can establish, of course, a direct connection. But if we want a strict access control to the service, in fact, other protocol, for example, like Megaco, would be more appropriated. So the third scenario, so this kind of scenario are real scenario in our context, in fact. So the third scenario concerns the access by the student to a lecturer or the teacher resource at a clearly defined time, what we call in French tutorat. So for this, the lecturer has to register in the register database all its potential locations, laboratory, office, and so on. This will avoid the lecturer to be attached to one terminal or location that give more flexibility to the service. Afterward, the client can send an invite, the student can send an invite to the SIP proxy, which in turn, by looking in the register database, forks the invite message to all possible locations of the lecturer. So receiving the acknowledgement from the lecturer's terminal, the client, the student, then can establish a connection for the media transfer with the terminal where the lecturer is. Okay, so this is this scenario, this animation. So we fork the request to all possible locations after receiving from the register database server the different IP address of the terminal where the lecturer may be, the potential location, and we can make a forking to ringing all the possible terminals. Okay. So to summarize, we have seen across few scenarios. Of course, we can imagine other scenarios that mobility, two kind of mobility, service level mobility and IP mobility can be an issue in the context of distance learning services. So SIP signaling protocol can be used in this context. Probably SIP is not the only alternative. Other protocol like H323 protocol can provide a solution, but using SIP from our point of view presents some benefits. So the establishment of user connection goes through SIP proxy. It's not mandatory, but provides some means for access control, logs, and security issue. SIP also is a standalone protocol, so it's possible or more easy to use with any other media transfer protocols. Data transfer in our context will be the first step, afterwards audio, and after we will put video depending on the performances of the internet, because we have students all across the nation. We have not an intranet, in fact, to connect all the clients. They have different kind of ISP, so we have to manage different access performances, so we have to deal with this. Also, a big advantage is that a minimal configuration is required from the client side, which is a big advantage for deployment access to avoid the problem of configuration of the client. Also, as SIP is a text-oriented protocol like HTTP, it makes its understanding and implementation quite simple for us in theory. But the cohabitation and interworking with other signaling protocols, because you have seen that we have other protocols in our architecture, H323, maybe we will have Megaco and other kind of protocols. And this interoperability led some question. For the moment, there are some problem of compatibility. We don't have some kind of gateways. Very difficult to find some kind of gateway between Megaco and other like SIP and so on. Of course, this solution has to be fully validated before deployment, as the student pass exam and they are in our university to learn and not to test the technology. So we have to put some platform to test, and after validate the solution, we can deploy. So that conclude my talk. Thank you very much.
Thank you, Ahmed. Is there any question? I actually have one question for you, which is not exactly a technical question, but maybe is of interest of people listening to you and willing to collaborate or maybe using the result. I've seen around the presentation a number of trademark or copyright signs. So one of the possible issues that could be asked is how much this product or technology is available to a community like anyone.
Tutelvisio, Tutelnet is trademark. We developed this software and this architecture, so it's that's why we put this trademark, because it's and it is accessible from the website of ENIC. We'll put this different software, but the software is not enough. Only we need also some hardware, some specific sometimes hardware, but mainly software.
Okay. There is no other question. We move to the second speaker, which is Mustafa Soy. Mustafa Soy is from the University of Erlangen in Germany, where he mainly deals with telecooperation and remote learning user interfaces. Mustafa was born in 1974, but I believe that he has also something else to tell us about himself. So Mustafa is going to connect these pieces, so I need to help you a little bit.
Thank you for this nice introduction, and I would like to welcome you to my presentation, and I'm glad to be here at TNC2001 and especially in Antalya, because of, as you can see on my name, I'm from Turkey, and that's a happy coincidence. I'm from this region, so I have to say Antalya'ya hoş geldiniz, according to Turkish hospitality. And like I said, hello everybody. Okay, now to my presentation, which has the title Videoconferencing with Advanced Services for High Quality Teleteaching. Today I will report of our research work about teleteaching at the University of Erlangen-Nuremberg, and I would like to present some of our results of this research work. Next, I will give you an outline of my presentation. The first point will be the motivation for teleteaching. and especially in our region. Next, I'm going to talk about our teleteaching infrastructure, and in this context, I'm going to talk about the network that we need, access points that we have, and our own developed teleteaching terminal, which is a main point in our teleteaching scenarios. Next, I'm going to talk about teleteaching scenarios at the University Erlangen-Nuremberg, and I just picked up some of those. One is a virtual lecture, a virtual excursion, and those two are synchronous scenarios, and we have also asynchronous methods called lecture on demand. We heard recently from it. And the next point will be future developments. I will give you some ideas that will be in present some research fields for teleteaching in the future. Okay. At next, I got a map of the area of Erlangen-Nuremberg in Bavaria. What we see is the geographical location of both cities and the link between them. The blue-colored line is our freeway, and the thin orange line is the highway between those cities. As you can see, the university with its different faculties is spread over both cities, and most of the faculties are in Erlangen, and quite few one in Nuremberg, and the biggest and important ones are in Erlangen the Faculty of Technology, and in Nuremberg the Faculty of Economics, Business Administration, and Social Science. In most cases, students need to attend classes in just one faculty, and that means they are in this one city. But there are a considerable number of students who has to attend classes in more than one faculty, especially students from the Faculty of Technology or the Faculty of Economics. So they have to travel around between Erlangen and Nuremberg, and obviously that's a waste of time, waste of money, human resources, and of course ecological damage because of the additional traffic that we have. So this geographical situation lead us to, in the early middle 90s, to make research in the field of teleteaching. And so we was on the way to look for solutions for teleteaching scenarios and make research in this area on need. And we still do. Okay. The next point shows our research objectives. So we have, of course, of the situation, research fields in synchronous and asynchronous teleteaching, and they are in use since many years. And what we now do is to try make the systems that we are and the scenarios high quality. So we are trying to make high quality media streams between the locations, and we are trying to go in the field that the user has a nice feeling with the technique. So both points are the main research subjects now at the university, and mine too. And next, I will begin with the network in our university and the connection to the gigabit high-speed network in Germany, the so-called GWIN. We see here the backbone of the GWIN that has a backbone of 622 megabits per second ATM line, and that will be enhanced in the recent years to 2.4 gigabits. Some test beds are in work, and they are going to improve the network, change the network step by step. So I think, I'm not sure, but I think we have also still have 622 megabits connection. From the central router in Nuremberg, we have this line, the ATM line to Erlangen, where the central router of the university is located, and from there and link to Nuremberg with 155 megabits per second. And we have also in our buildings in Nuremberg Ethernet 100 megabit is common, and our ATM line with 155 megabits. So I told this because we make some virtual lectures in the house, so we transmit some lectures from a lecture theater to a conference room, and that's important. The next slide shows you our access points, and how does the access points look like, and where are they located. You see again those two cities, Erlangen and Nuremberg, and right, in Nuremberg we have our lecture theater, which is the main location for our virtual lectures and virtual excursions. And we have also well-equipped conference rooms in Erlangen and also in Nuremberg. And the access points in the slide are not just a plug-and-play socket that you put your plug in and it works. It's more special equipped conference rooms and this lecture theater. And in those locations we can capture different audio-video streams, mix them, and transmit them with special codecs to each other location. And I will list some of the media streams which are transmitted for a virtual teleteaching event between the parties in the slide. So we see the lecture theater in the middle, and in the back side, and two conference rooms. The base for the transmission is of course the multicast network. In our case we use ATM and TCP IP. TCP IP is used for data transmission, especially for distributed presentations. And to establish the teleteaching session, we set up at first M-bone session between all participating parties to guarantee the communication between them. And with the beginning of the event, it could be a virtual lecture or a virtual excursion. We transmit a high quality audio-video media stream from the lecturer, who is in the lecture theater, to each conference room. Can we put the light out, please? Okay. Okay, with the beginning, we sent a high-quality audio-video stream to each conference room from the lecturer, who is obviously in the lecture theater, and to each conference room. In the conference room, there are remote participants for this lecture. The last media stream that we okay, I forgot this one. We also transmit the remote presentation. It could be a PowerPoint presentation. It's common. The last media stream that we transmit is a medium quality video stream for additional material, like a video presenter or overhead slides, or a video or DVD movie, so that all the media stuff that we use in the lecture theater and give access to our local students, they have also we transmit them to the remote students. And at next, I will show you the infrastructure of the infrastructure and the concept of our multimedia lecture theater. In front, you can see the lecturer with common presentation devices like an overhead projector, a notebook, a presentation computer, data beamer, and so on. And additionally to these devices, we can see spread over the lecture theater some cameras, microphones, and loudspeakers to capture different audio-video material of the audience and, of course, of the lecturer. At the back, we see a control platform. For all different kinds of media streams, and a media mixing desk to combine the important material for a virtual lecture. So that's the most important and intelligent part of this infrastructure, I would say. And in most cases, we have a technical assistant to operate all the elements of the control platform. For the handling of the platform, we need special technical skills, and that's why we need a technical person who needs technical skills and knowledge of connection between the operating devices and so on. That's the hardware components that we need and use for teleteaching events. And now I'm gonna show you some of our software components. The first one is some N-bone tools. I think it's known for medium quality video conferencing. So we have 3 tools: SDR for session creating, VIC and VAC, I think, for video and audio, and a whiteboard to draw on some stuff. Okay. Next one is video conferencing software for ATM. It's high quality. This are some software components for the codecs and for our video grabber cards of our Sun workstations. We do need some shared applications, distributed presentation systems, like I said, PowerPoint, and so on. And of course, support software for controlling the hardware, and that's the main point of our research that we are developing. This slide shows you an ATM-based teleteaching. To just give an overview, we have on the left left-side camera is conducted through an audio-video encoder. We capture the video signal and encode them with the encoder to native ATM AAL5 packets. They are connected to an ATM switch, and other decoders and encoders also are connected to other ATM switches. So we put the signal, we capture the analogous signal, code them, put them over the network, and the decoder decodes them, and then we can show in each access point the video or audio material. So the next slide is just to give you a feeling of computer-based learning. For us, the important two fields are distributed synchronous teleteaching and distributed asynchronous teleteaching, and those are our main research fields. And I'm going to focus today to distributed synchronous teleteaching, telelearning, and that means interactive live broadcast of lectures. And how does it look like, such a scenario? I have this tree-layered model. In the middle, the university as producing factory of knowledge with lectures, practicing course, and seminars. And at the end ring, we see some customers like companies, research institutes, educational facilities, universities, who wants to export or buy this knowledge. And you can see those different methods of teleteaching, like distributed lectures, information and service center, distributed training, virtual excursion, and so on. I'm going to focus today on distributed lectures, distributed practicing courses, and how it's said, lecture on demand, teachware packet. But the first one will be our subject. I got here a screenshot for you, one of our virtual lectures. What we can see here is the lecturer with her presentation material, in this case an overhead projector with some slides. She's also using a whiteboard, and in this field you can see here some of the stuff that I don't want to. I'm sorry. Oops. Okay. You see in the right side the lecture, and on the left side the students. Those first on the top are students in a media lab who are attending the course, the lecture over Sun workstations. They have a video grabber card, so they get the video signal, and this whiteboard application, this N-bone tool. We see in the middle the lecture theater in Nuremberg, and some students attending the lecture, and one student in the end of the line. She's also attending the lecture, I guess from home or something like that. What we do is we transmit the audio and video signal of the lecture to each of these points in the lecture theater, in the multimedia lab, so that the students get all the stuff which is presented in the local theater. This one is a virtual practice course. The students can invite at special times an tutor, an assistant, to help him, teach him, and they can communicate over a video conferencing system and use a shared application, a text editor, so that they can see each other's fails or comments in the field. You can also do virtual seminars. It's quite the same like a lecture. You see in this part, in the middle picture, the speaker, and left and right of them, the participating parties, and at different places. And in the middle, the big one is the slides that is showing now. And those is the same, just in our multimedia conference room. The multimedia conference room looks like quite the same like the lecture theater that I have introduced you, and the main different in this picture is the Teleteaching terminal, and that's what I'm going to talking about in the next slide. Our Teleteaching terminal, like I said, is one of our main points that we are going to work on. This is a picture of them, and what we have tried is to integrate different devices in this terminal, so the lecturer can use them without knowledge of any connection and any special technical knowledge of the devices. So we see we have there a presentation control PC. We have a touchscreen monitor, touchscreen for presentation. We have a touchscreen for media control. We have an auto-tracking camera for the lecturer, so the lecturer can move on in front of the terminal. He's not bounded in a special area. We have our video presenter for additional material like overhead slides, or to show some shapy things, whatever. A video recorder to show videos or record the lecture session that we made, and DVD player, of course, and we have control monitors for the video stream. In this control monitors, the lecturer can see the outgoing signal for himself. He can see the remote participants of the right side on this screen, and he can see the additional video stream that's going out. Okay, and how does it look like? I have here two conference rooms, where in one is our Teleteaching terminal, and we send one audio and video of the audio stream of the lecture is high quality, our ATM. We have a loop of audio video streams, medium quality of the audience. We also transmit this additional video, and of course the distributed presentation. And we have also in the local conference room media streams to control, to connect with each device, and that's the main point. We had in the lecture theater this technical assistant who managed this stuff. But in the teleteaching terminal, we have integrated this in a media control system, so that the lecturer has the opportunity to control all stuff for his own. So, like I do today, I'm coming here and I want to give a presentation with my notebook, and but I don't know how does it work with the beamer and so on. And in our system, you come and you have the media control system, so you click on the left side in input devices, notebook. You see on the right side the security benchmark, and then you choose a output device, in this case the beamer. The security is okay because you can connect the notebook with the beamer. And then you go and execute connection, and you have the connection, and you can go on with your presentation. You can also save some standard configurations that you ever use, like I don't know, you use your notebook and a video recorder, a video presentation on the TV, so you can choose one of those standard configurations, and on the right side, so you get this, and like the same way you click on execute connection and you have the connection, and afterwards if you are at the end of your presentation, you go on disconnect, so the connection is over. Okay. The architecture of this system looks like this. We have the view as this is the GUI, and device manager is connected to the devices, and connection manager is controlling the connection. The middle term is in security manager, who's checking out the possible connections, if it's possible or not. The last one, DI, is driver interface, and we have a persistence manager who looks in the database to give the view to the GUI. Okay. The second point was the lecture on demand teachware packet. I'm going to give you just a quick overview what we do. The analogous video material that we captured in the virtual lecture, we are trying them to digitizing and editing, so that we get a synchronizing of slides with a video stream, and then put them in an online presentation. And how does it look like? It's the same way. The lecture is in the middle. We capture the audio-video signals. We put them over an audio-video mixer. And what we are now trying to do is to automate the stuff that we don't need a technical assistant at this point, that we can put the media stream in the encoder and in our repository. And this action looks like this. So we got the digital video, and we enriched this video material with slides, websites, graphics, animations, and so on. And therefore we have a special lecture on demand authoring tool, and the end product of this is a digital lecture, so we put them on our repository, and like I heard before, on our lecture on demand server. Okay, the last point, what could be future developments? Improving controlling capabilities, integrated device control system. That's our media control system where we're going to work on. Second point will be improving interaction quality. especially in virtual teleteaching environments, synchronous scenarios, and we are trying also improving video and lecture on demand quality, and in this case especially DVD production is our main focus. Okay, I think that's all. Thank you.
Thank you, Mustafa. Is there any question on the floor? I do a very quick one for you.
Yes.
You are using for the high quality video, of course, ATM.
Yes.
What are the plans to eventually replace it with some of the emerging quality of service stuff, providing that probably in some time you will have IP only networks?
What we are also do is video conferencing systems over ESDN, but we don't have yet any solution for IP concept.
Thank you, Mustafa. Yeah, one question over there.
It's about 10 to 12 megabits per second.
Any other? If not, we move to the last presentation, which is going to be brought to us by Markus Berg. Markus Berg is an electronic engineer who works in the German Institute for Broadcasting Techniques. And as in the previous presentation, we have seen something where a video broadcasting system in a university looks like television. In this presentation, we will see what television can do, real television production can do using the network. One of the main areas where Mark is active is the quality of service related issues on networking, especially focused on the problem that broadcasting on real time has got for television. So as soon as we are reconnected back, I leave the floor to Mark.
Thank you. Thank you for not being at the beach. So I try to keep my 30 minutes and talk a little bit about, if it's on screen, production of television and movies in high-speed networks. Okay. Just find my presentation. Not too fast. So it's called, should be called, Distributed Production in High-Speed Networks. Mikrofon ist angeschaltet normalerweise. Geht's jetzt? So, do you hear me? But the problem is this. No, thank you. I'm talking about distributed co-production in TV and movies. So just to introduce the project, I will show just some slides. Then I'm going to talk about why we have to use ATM in this area. Then we had made lots of tests and experiments with ATM for broadcast and production applications. I talk about this. Then come to the Gigamedia project, which is running on the German Research Network, which shows such an infrastructure, and then conclude the lecture. So just a short acknowledgement that the German Ministry of Education just founded the project. So, just to start, the project partners in this project are first Das Werk in Munich. This is a real production house, so they're making movies, commercials. Just actually they are doing the new Stalingrad movie. It's a $100 million movie. And for this reason, they are a little inactive in the project at the moment. The second partner is the GMD, is a research institute in Berlin. In our project, they are doing the remote measurements on IP basis, web-based measurements, and are dealing with some streaming protocols. Then the Heinrich-Hertz Institute, also in Berlin, they are mainly doing the format conversion of video and MPEG-4 streaming. And last but not least, the IRT, my company. We are the Research and Development Institute of all the public broadcasters in Germany, Switzerland, and Austria. And so I have many departments, starting from satellite management, frequency planning, microphones development, and I'm working in the network and network management department, and this is the partner of the project. So what are we doing in GigaMedia? Well, we build a network and build applications for the distributed production of TV and movies based on the Deutsche Forschungsnetz, the German research network, where we develop new applications, we test them, and of course we do it and show it in a whole complete scenario, just from the start of the production to the end customer of the film and television program. So, just a short overview how the network is looking like. At the left side, you see the Berlin campus. All the partners are connected at the moment with ATM 622 megabits per second connections. And the right side is Munich, where we have to go over a local city provider in Munich to reach the German research network. And you see GMD Focus has 2 locations in Berlin. They are also connected via ATM. So everybody is talking about IP. IP over everything, everything over IP, IP over fiber, copper, IP over water. We had to choose ATM. Why? So TV and film production has almost the highest requirements you have for networks. So the first point, and this is the most critical in most networks, is jitter and wander. When you work uncompressed with digital video, you have 270 megabits per second. The requirements at the studio side for jitter are in the nanosecond range. So not all networks even think about coping with this issue. I'm coming a little bit later to the point how you can do it. Latency is, of course, when you have interactive services, you cannot afford a long latency. I think of an example. CNN recently had a good idea of making an interview between a politician in Moscow, a politician in Toronto. They switched them over satellite to the CNN studio. And, well, for interactive talks, you need skilled people. You have a round-trip delay of half a second, and you cannot start talking immediately after when your partner is talking. Well, politicians usually don't do it. They had to stop this interview after 5 minutes because there was no conversation possible. Everybody was talking at the same time. Even the moderator in CNN was a very poor man. He couldn't even get them stopping. It was very interesting. Next point, if you don't want your transmission to be interrupted, if you show the final of the World Football Championship, well, it's not good if you have long interruptions. Then the same point is with error ratios, should also be very low. For production, there is a standard you need 10 to the minus 14 is allowed for uncompressed production in film production studios. Of course, you need point-to-point connections if you connect to studios, or point-to-multipoint if you distribute a program from one studio to different playout centers. The next point, easy management for a complete scenario. Well, I don't think we ever achieved this because every vendor makes their own management. You need high-speed file transfer between video and audio servers. That will be more and more important because more and more movies and so will be stored on files, and they can be transmitted via file transfer, not in real-time transmissions. And of course, the availability must be high. If you have an important event, you don't want a message no route to host or such things. You want your connection immediately. So ATM is the point. It's the it's the best technology. They guarantee for the whole duration of a connection the quality of service you request, bandwidth, timing issues. You can keep the jitter of ATM connections in a very tight range. We established for the first German television program a network between Hamburg, Frankfurt and Munich on STH and ATM. And due to GPS synchronization of all the components, we had a round jitter of this connection about 9 nanoseconds. And with this jitter, every production tool can work. ATM because the ATM equipment is very fast, has low latency for the transport, and at the moment in almost every European country the biggest carriers, Deutsche Telekom, Swisscom, also Telecom, and even Williams in the United States, they build ATM networks when they want to offer a broadcast service to broadcast stations. So ATM is the best solution for the quality of service we need in our production scenarios. Now IP, well, IP started as a best effort service. Don't ever talk to a video engineer about his video will be considered best effort. He is running away or he will shoot you. So the solution many carriers were talking about in the last 2 years is throw bandwidth at it. Well, this year they are not shouting so loud anymore because they learned about the problems when lots of people want to view the same multimedia content. Last year the European Song Contest was a disaster. EBU had made lots of advertisement for everybody could see it on the internet. Well, I think 3 or 4 people could see it. 500,000 tried it, and even the director of EBU couldn't hear a single song in the internet. So at the moment there is a lot of good work done at the IP level with new protocols, RSVP, DisServe, but from the point of view of our side, the production, this is class of service, not quality of service. You can prioritize certain classes of traffic, but not a single traffic stream. So it's not, at the moment, not good for our purposes. MPLS, well, is a very good approach for traffic engineering. Some people talk about MPLS providing quality of service. That's not, but it helps providing class of service. And even if you give some IP streams a higher priority, they can disturb themselves in the same class. So IPQR's problem is not yet solved, but there is a good work on the way, and perhaps in a few years we can use IP for our purposes. So the main point in the Via Media project is the transmission of uncompressed digital video signals. It's the SDI standard, 270 megabits. It's including uncompressed video, uncompressed audio, and some metadata in the stream. The whole transmission on 2 of these adapters has 300 microseconds, so no problem with real-time interviews. And you can use it for distributed production, interviews, telemedicine, and telerobotic, where also high interactivity is needed. That's the box. You can buy it from us, but that's not the case. So the tests we done in the last, let's say, 2 or 3 years with ATM for broadcast applications were forced by our broadcasters in Germany. They wanted to use networks for interconnecting their studios and their playout centers. And we are not only making lab tests, we make big tests in real wide area networks. So the first test was one of the biggest in Systems 2000. Systems 2000 was a fair in Munich. So there we built up a multi-service network platform for all kinds of broadcast applications. We had a dark fiber connection between our company, the IRT, and the Munich fair. We used WDM with 3 wavelengths. We put 2 times ATM STM4 and 1 time ATM STM1 on those links. And then we showed different applications. The first application was the uncompressed transmission of digital video. Like I showed it on the last slide. We connected a TV studio at our company to the booth and made interviews with some skilled people from broadcasters. We have the Bavarian broadcaster right around the corner, so we invited some of their reporters to talk to each other over the network. They were very surprised how good it works. They could really interact and talk to each other. And we also made a little video clip in our studio and retransmitted it to the booth at IBC. So we could both made interviews and the production scenario. And the funny thing is, I don't know if you know the German news sender NTV. They make every week a transmission from Tel Aviv via ISDN. So this reporter is the poorest man at NTV because he stands all the time like this, doesn't dare to move. So with a low quality ISDN transmission, he makes his comment. 5 minutes, 10 minutes, and then needs a massage. And he even has grown a beard, so we don't see his lips. And his boss was at our booth and was saying, oh, we would need that, but they don't have the bandwidth. That's one problem at the moment. But it's getting better. So what we showed also was distribution and contribution of television programs from our company. We collected several programs, compressed it to MPEG-2, 42 at bandwidth between 4 and 18 megabits per second to show the different quality of the video signal. Then we had high-speed file transfer to interconnect our archives, our video archives, and encrypted the video data to just via ATM, just to show that there's no access from the outside, and connected our fiber channel arrays located at IRT to a PC at the booth. So the PC just thought that the remote fiber channel array was a local hard disk on the computer, and we could go with Microsoft Explorer and look at the files. We also made the video and audio streaming at low quality with the Windows Media Encoder and the real encoder, and we had a fine measurement of the delay time. So the uncompressed video from our studio to the booth took about 1 millisecond. The MPEG-2 decoded video with encoding and decoding took about 120 milliseconds, and the IP stream was there after 15 seconds, because that is the case when you use the streaming. It's mostly the buffering at the receiver. And we had also remote management of our ATM network from the fair. So this was the network. At the right side you see the booth at the systems, where we had a large plasma screen, camera, the ATM equipment, and on the left upper side is the IRT, where we have our studio. It's called UniTV Studio, and a local area network, which is also ATM. In the middle you see the city network of the city provider Ahmed, and on the lower side you see a German research network where we connected for the fair the University of Erlangen, where a lecture was transmitted live from the university to IRT, and we reconnected it to our booth, and then people could also talk to Erlangen at this time. Here's just an overview of the applications, and the most important thing here is that we had a multi-vendor network, so we had integrated several different vendors, Cisco, Adva, AT Media, and so on, ATM switch from IBM, to our network, and it worked properly. A similar thing we made at IBC 2000. Now we had a wide area connection between Munich and Amsterdam, showed mostly the same applications, also these interviews and distributed production. We had again our studio, and now we had a reporter at our booth making live interviews with people in Amsterdam. We make a little movie clip at the IRT, and then transmitted it back over the ATM network to our screen at the booth, and so people could afterwards judge the quality of the produced material. So not everybody has a good fiber connection to their premises. Some people are only reachable by satellite, and therefore we tested also ATM over satellite. We cooperated with the European Broadcasting Union to make a transmission between Munich and Geneva. We used the Eurovision network, and we combined an SDH ATM network terrestrial in Germany with the EDU network. I'll show you a little bit later a picture of the setup. We transmitted two television programs over an unidirectional E3 link, and we made video audio file transfer on a bidirectional E1 link to megabits per second, even with high round-trip delays which you have over satellite, and we managed the whole systems remotely from the IRT. So at the left upper side is the IRT. We had the D1 is the digital video source. We had MPEG-42 encoders, an ATM test system to measure delay and such things, and the file server. Going over a layered network. This is a network momentarily built up by the first German television program. It's a provider layer, only optical networking bought from different providers. An broadcaster layer is SDH, which is controlled by the broadcasters, and an ATM layer also controlled by the broadcasters. We went from Munich to Frankfurt, where the satellite uplink was. We went via the Eurovision network to Geneva, and at Geneva we had the same infrastructure as Munich, but only the receiving end. So what was at this time very surprising, we had only a few satellite slots, and when the satellite connection was there, everything was working. So it's very easy to set up those ATM connections, and there was no problem transmitting those television programs. And the file transfer, we used a native ATM protocol called ATP to cope with the round-trip delay. We make a test with standard TCP/IP, and we had on this 2 megabit link only a transmission rate of 12 kilobits per second. It was not very satisfying, and then we used this ATP protocol, and we had a 1.8 megabits per second on the same link. And we made also another test when we turned down the power of the satellite uplink, so that bit errors occurred. We transmitted the video signal with AL1 error correction, and it worked very fine. And even with a high error rate, the file transfer and the management control was still working. So now we come to our current gigamedia applications. We prepare at the moment a large demonstration which shall start next week. We have our next meeting. Production of commercials for supermarkets. And there the production house cooperates with the post-production house sitting on the same network, sharing resources. All partners, even the client, are connected to the same network. So between the production houses there's a transmission of uncompressed video and file transfer then to the customer, which can talk always over video conference with the producers. The scenario we will build up looks like this. The production house will be played by a Heinrich Hertz Institute, the post-production house will be played by us, IRT, and the customer will be played by the GMD. Every location has a video conference system where at any time they can talk about the product. At the production house there is of course the production environment. You see at the left side, camera, recorder, and mixing infrastructure. Then they have a format converter, so the stuff will be transferred into MPEG-4 for previewing and MPEG-2 for storage on server and distribution on CDs. The post-production house has, of course, the post-production equipment, so we can mix additional stuff, we can introduce special effects, and also a video server to store the file. And the client will only receive an MPEG-4 stream to preview the stuff, and after video conference, after everything is said and done, he will receive MPEG-2 file for distribution. So this is the workflow. First, the production house shoots the film, stores it on recorder, transmits it to the post-production house. Then we talk via video conference what is to do, send it back to the production house. Then they will compress it onto MPEG-4, send it to both the post-production house and the client, and then there is a conference between all three of them. And after everything is okay, it will be transformed onto the final mode, MPEG-2, and then sent to the receiver. And we also included a possibility for the post-production house to remote control the video recorder in the production house to view the uncompressed material live without having somebody sitting at the recorder. So just to go a little bit more detailed into the stuff, this is the distributed post-processing. So you can distribute the files from one video server via the gigabit network to both other locations. The same thing is with the streaming. You can have two different video streams going to two different locations, or in another case you can have the same video stream going to every location with a video conference included where everybody can talk about the quality of the material. And just before the end, another thing just to improve the streaming, You have at the moment some different methods of transmitting data. Reserved is very clear. You have reserved bandwidth and transmit the stuff. Elastic is best effort. Then you have a combination of both. And the GMD is trying to improve this hybrid version by creating a hybrid adaptive version using larger buffers at the receivers. So you send with a reserved bandwidth the first part of a stream, then look at how the buffer is standing, and then depending on the buffer you send reserved or adaptive or elastic. So this should reduce the resources used on the network. We are preparing tests. We didn't have tested it over wide area network at the moment, so we're not quite sure how much this improves the streaming. So coming to my conclusions, the distributed production of film and TV definitely leads quality of service networks and high-speed networks, and at the moment this is ATM. Giga Media project has built up the infrastructure for this network, including video conferences and preview in lower quality. And the key application is the uncompressed transmission of digital video over ATM. And we also developed remote control of digital video equipment. At the moment, ATM is the only technique that fulfills the requirements that we at the production side have for networks. And IP, at the moment, cannot provide solutions, but for some applications, low bitrate streaming and file transfer, IP is inevitable. IP is there and IP will be there. And adaptive streaming is a good and cheap alternative for reserved data transmission if this algorithm works properly. So this concludes my presentation with some thanks to 3 colleagues who helped me. And if you have any questions, you can give it to me now or contact me later. Thank you.
Thank you, Markus. Is there any question? Egon.
I have 2 small questions. The first one is, what kind of codecs for MPEG-2 are you using, and what's the video server? And the second one is the MPEG-4 that you mentioned. Is that the ISO MPEG-4, the latest version, or the Microsoft MPEG-4?
No, the MPEG-4 is a development by ENIC Institute. They make their own MPEG-4 encoder and decoder, and they have introduced it into the project. And for the MPEG-2 encoding, we use all kinds of vendors. We use Thomson, we use Philips, what's available. So we didn't see lots of differences in the MPEG-2 encoders at our bandwidth. We were at the demonstrations. We normally operate at 8 megabits per second, and the quality is enough on every encoder, every vendor. Video server, we had a video server from Sun. It did not work so good. At the moment, we use electronics profile for the video server.
Is there any other question? Yes, over there.
Yeah, I wonder why you're using for transmitting the lossless data totally uncompressed video. Is it the latency?
No, the production houses told me they want every bit of the video back.
Well, you could lossless compression. Could do a lossless compression.
The compression technology is available and not mathematically lossless. We make measurements, we didn't get every bit back. So there's at the moment no absolute lossless compression. That's the problem.
Don't see any other questions, so thanks again. Oh,
Yes.
Egon, again.
Just as a comment on your last answer, why compress it all then?
We don't compress it. Just MPEG-2 for the preview and for distribution to customers.
You said MPEG-4 for the preview and MPEG-2 for distribution.
Yes, we use MPEG-4 for the preview and MPEG-2 for distribution to the customer, so for DVDs or so. You cannot put it uncompressed on DVDs.
Okay. Are you looking into other type of signals, HDTV for instance?
At the moment not.